Alright, hello scholars, it's Mr. Who back at it again with part 2 of rational functions. So, last time Miss Atkin presented you some details, starting details, the intercepts, for example, is one of them, and also some holes. Now, there are a couple more features we haven't talked about yet, but you may have already seen them in the parent function. And it's those little parts we talked about earlier about the approaching business. They weren't on delta math, but it was mentioned in the video. Okay, when you take x out to certain values, the graph seems to approach, or the graph, I should say, the y values approach the certain value, whether it's infinity or 0 if you're talking about the parent function. But either way, we're going to talk about those a little bit today, and they're known as asymptotes. So she did mention that a couple times when talking about this, but we're going to talk about how to find them. Okay, how to find them today. So today we're talking about asymptotes of rational functions. Alrighty, so get out your notes here and let's go ahead and get started. So the first thing we got to talk about, okay, this might be a little bit of a reminder from last time. I'm going to bring up a function that Miss Atkin used, and she was talking about the whole, okay. So this is her function 2x plus 12 over x squared minus 2x minus 48, okay. So if you remember from your last time's notes, she was using this function to show you how to find the whole in a rational function. So the first step here, okay, number one step is to simplify, right? So when you do that simplification, you have to factor first, right? So the top becomes 2 times x plus 6. This should all be reviewed, so I'm going to go ahead and just blow through it. But if you need help factoring, definitely ask to get some practice in on that. Okay. But at the bottom, use an ACV tree. Ends up at x minus 8 times x plus 6. Okay. And remember, to get the whole, we cancel these. You already see they're the same, so we definitely can take them out of the top and bottom. And so we're left with 2 over x minus 8. Well, last time we talked about how when x equals negative 6, okay, that's the thing we canceled out. That's the factor we canceled out. And so that will give us the whole's coordinates, or what we should use for the whole. But what about this guy right here? This x minus 8, what do I call him? Because remember, we said that when the denominator is 0 in a rational function, that's where the rational function is not defined. Okay, and this actually will give you the vertical asymptote. Okay, and specifically for this example, this vertical asymptote will be at where x equals 8, right? That's what I solved for x there. All right, and that's really all you got to know. This is the asymptote itself, the equation for such. Okay? It will always be a straight up and down line, hence why we call it a vertical asymptote. And I'll show you that on Desmos here, and I'll also go through a couple more examples to make sure you know what you're doing here with that. Alright, so here we are on Desmos with my equation that I plotted in here, the original one, not the one we simplified to. Very important when you're trying to check your work in Desmos, use the original one, because that will tell you everything you need to know. Okay, and so I've got these points here in the table, and we can see that at 8, it's undefined. We know this because the denominator equals 0 in that space. Now remember, the whole just looks like a point. It's a point on your function, right? That just doesn't have a value, undefined value. Okay. That's why we call it a whole. But in this case, x equals 8. That's going to be a line, a vertical line straight up and down. And when I toggle this, you guys can see, hopefully, that the graph itself, I can even zoom out if you need me to. Okay. The graph itself seems to avoid touching this line. Now, I know it gets pretty close here, but it doesn't ever touch. Doesn't ever touch. And that's what we call a vertical asymptote. So it will simply be the place in your function after simplifying, okay, where your denominator equals 0 still. Okay, that's everything about the vertical asymptote. You can have more than one, just so you know. Okay, it's not like every graph has to have one, and you can even have 0. That is also a case. Okay, so let me go ahead and head over to Delta Math, pull up an example problem, and lead you how to solve it. Okay, so here we have an example of our rational function, and we want to find the vertical asymptotes algebraically. Okay, so on this problem, you'll probably see there's a couple of different things going on here, but we are basically going to be following what I just told you. We're going to simplify the function, okay, and then we're going to find out if there's any holes. Okay, so let's go ahead and tackle this one. Find the vertical asymptotes of the following function: f of x equals 3x squared minus 3x minus 36 over x squared minus 6x plus 8. All right, well, in the first step, okay, simplifying, you got to factor these top and bottom first. So let's go ahead and whip out that trusty factoring methods of ourselves. The top looks like everything I can take a 3 out of, right? Hopefully you should see that. I'll be left with x squared minus x minus 12 on the top. On the bottom, I've got another ACB tree type thing. This one's actually pretty simple, I think. X minus 2 and x minus 4. Now, I'm going to tell you right now that if you're not so great at factoring, okay, that's not actually going to be a huge problem, okay? It's not actually going to be a huge problem, because what's nice about most functions we're going to take a look at in this class is that you can reasonably expect it to cancel 1 or 2, and maybe not if you can see that. Okay, but since I'm looking for these two things in the bottom in my denominator, you might think about trying to factor this top one with one of these in mind. All right. So let's think about it here. I'll just go ahead and do the ACG tree out right here. I got an a times c, negative 12. Break it into two pieces. It's got to add up negative 1. Well, I know that negative 4, okay, down here is one of my pieces. So what does that multiply with? 3 to get negative 12 and add to get negative 1. Well, that's perfect now, isn't it? So this again will go into 3 times x minus 4 and x plus 3. A very nice factorization. Okay, that's over x minus 2 and x minus 4, of course. Okay, so now at this point in time, I can say for certain that these are going to cancel for sure. And what I'm left with is x minus 2 all alone in the denominator. So going back to the problem here, I'm going to use my mouse because it doesn't work. Okay, I didn't fully simplify it. I didn't cancel these and then make it nice and pretty. Okay, but for finding vertical asymptotes, you don't need to do that. Okay, so this Delta Math module wants you to select from a couple of options no 1 or 2 vertical asymptotes. Now, in this case, I only have one factor remaining down there, so I'm thinking 1 is my answer there. And then it wants an answer. It wants an answer. Now, here's how you should form your answer. Okay, you need to type x equals first, because otherwise it's not a function, right? It's not a line. And you need to put whatever value makes the denominator 0. In this case, it'll be 2. If you put 2 minus 2, turns it to 0, and that's how we get our answer here. So I'll click submit, and I got it all right. So that's the basic way to do this. You could end up with multiple vertical asymptotes. Remember to simplify first. Okay. You could end up with no vertical asymptotes. It all depends on the problem you're taking a look at. Okay. So that's pretty much all you got to do for that module. Now next up, we're going to talk about horizontal asymptotes. These are a lot harder, so I'm going to take a little more time talking about it. All right. See you then. All right, welcome back. Here we go. We're going to talk about the horizontal asymptotes. Now, we're talking about identifying horizontal asymptotes compared to vertical ones. Okay. The vertical ones going up and down, of course, is an easy identifier, but the horizontal ones go from left to right. Okay. And once again, just like the vertical asymptote, graphs don't necessarily, or rational functions, sorry, do not necessarily have one of these, but it's not possible to have more than one. Okay, at least I'm pretty sure there's no way to have more than one. So it's a little different from vertical in that sense. But the main way to identify horizontal asymptotes is by degree of your numerator and denominator. Okay, so when I talk about the degree on the bottom here, I'm going to label it here, I'm going to have 3 different types of rational functions, okay, based on whether the degree on the bottom is bigger than the numerator. Okay, on top, I will be a place where, okay, they are equal to the numerator. Okay. Or the last case would be if it is less than the numerator. Okay, so remember when we talked about degrees, we're talking about the exponent, the highest exponent. So in the bigger than case, if that example, I'm going to show you right here, okay, if your denominator on the bottom, we can just use the example up there, is greater than the numerator. So, for example, our first one that I had up there, 2x plus 12, all over x squared minus 2x minus 48. The degree on the bottom is 2, the degree on the top is 1, so the degree on the bottom is bigger than the numerator. If that is the case, there will be a horizontal asymptote existing. Okay. But it is very simple to find. You just say y equals 0. Okay, y equals 0. So no matter what, if your degree on bottom is bigger than your numerator, the horizontal asymptote is always y equals 0. It's pretty easy that way, huh? So don't have to think too hard about it. Now I'm going to go to the right. I'm going to go back to the middle one in a sec. But let's say the degree on the bottom is less than the numerator. So for example, we have f of x equals, let's just flip this around, 3x squared minus 2x plus 5 over x minus 2. Let's say you have a rational function like that. Well, obviously the degree on top is 2 and the degree on the bottom is 1, so my bottom degree less than my numerator. In that case, there is no horizontal asymptote, and I'll abbreviate HA there. Okay, that's also really pretty easy. Okay, so with either of these two cases, you don't have to do a whole lot of computing at all, if anything. Okay. Now the last one here is the tricky one. Okay, so pay attention to this one. If you have an equal degree on both top and bottom, so here's a random example for you. Okay, I'm going to go ahead and say 3x squared minus 2x plus 5 one more time. But instead of having x minus 2 on the bottom, I'm going to put 4x squared minus 9. How's that? Okay. Well, degree on the top is 2, degree on the bottom is 2 as well, so they're equal. Then you have a horizontal asymptote. Horizontal asymptote exists at, okay, this is the part where it gets tricky, okay, leading coefficient of numerator over the leading coefficient of denominator. So, in this example here, my horizontal asymptote will be at the line y equals 3 over 4. Okay, so that is because I'm taking a look at my leading coefficients, the coefficients attached to the highest degree term in my numerator and denominator, and that's how I got 3 over 4. Okay, so there's not much computation there again. You won't have to simplify this or anything. You should definitely be looking at the first form of your function, not like the vertical asymptote. But the hardest one is this middle one. If you see the numerator and denominator having equal degree, you're going to have to think about their leading coefficients too when determining what the horizontal asymptote is. Okay. And again, just like on the graph, it just displays as a nice horizontal line that the graph cannot touch. All right. And for sake of time, I'm just going to go ahead and move on to the Delta Math examples. If you want to check any of these graphs out, I would recommend plugging them into Delta Math and seeing them for yourself. All right, and I'm back here with the Delta Math. So for this, it's going to be pretty simple, I think. Okay, it's basically just I got to think about whether its degree on the bottom is bigger or not compared to the numerator. Now, of course, this is the teacher side of things, so you get to see that. But the degree on the bottom is bigger here for sure. Remember what we said about the bottom being bigger earlier? Okay, if it's bigger on the bottom, then there is going to be one horizontal asymptote. It will actually ask you for no, 1, or 2. This shouldn't ever be an option, I'm pretty sure. And if it does, you can, hound at me for giving you some incorrect information. But this should lend us to having one horizontal asymptote, right? And it's going to be at y equals 0 using the rule. That's a 9, not a 0. Okay. Let's check if I'm right here. Y equals 0, and I'm correct. Okay, so whenever the degree on the bottom is bigger, you don't have to look at anything else. You can just say, all right, I'm pretty confident. Y equals 0. Let's go with it. Okay. So now I'm going to look at another one. Okay. Degree on the top is bigger. Let's go with that one. Okay. So with this problem, I've got a 2x squared minus 2x, 5x minus 5. If I take a look at this top, obviously it's degree 2. On the bottom it's degree 1, right? And remember what we said from before, if you've got a degree that's higher on the top, okay, lower on the bottom, you just say there's no horizontal asymptote, and that's the answer there. Bada bing, bada boom. Alrighty. Not bad, not bad. And finally, of course, if you've got a degree equal, okay, I'm going to go with the unfactored one. Okay. Find all the horizontal asymptotes for the following function. Okay. Remember, we did say there was one horizontal asymptote for these ones, and it was going to compare the leading coefficients. So take a look. Let's confirm that they're the same degree. X squared on top, x squared on bottom. Degree 2, they're the same. All right, but I'm taking a look at that leading coefficients. Those are definitely not the same. All right, I got 2 in the top and 3 in the bottom. All right, so if I'm comparing those together, I'm going to have that y equals. That's so important to have, so make sure you have that when you're putting the answers in here for the horizontal asymptote. And then I'm thinking, okay, leading coefficient. Top is 2, and I'm going to put it over the bottom one. Okay, so just go in order there. Let's take a look on if this is correct or not. And bam, there we go. Okay, so that's pretty much all you're going to be responsible for this section. Okay, this section of Delta Math anyway. And that's pretty much all there is to talk about with finding asymptotes and stuff of rational functions. All right, and that is everything you need to know about horizontal asymptotes, vertical asymptotes, asymptotes in rational functions. Okay, so I'm putting this here again just so you have it in a nice convenient place to look at. Actually, I need to move off of that here because you can't see what it's titled of. Okay, but vertical asymptotes, again, you're going to need to simplify. Horizontal asymptotes, you got to compare your degrees. Okay? But outside of that, we'll talk more about this in class, especially if you got any trouble with the IP that comes up. Okay, we'll see you then. Take it easy.